So at a glance, without doing any calculations, are you able to determine whether or not either of these matrices are singular? As in, or do these, which of the two matrices have an inverse? Go ahead and pause the video and really look at it without doing any math. And it turns out that because A columns 1 and 2 are multiples of each other, that yields a result of a determinant of 0. And B is some scalar. And when the determinant of a matrix is not 0, that would indicate that the given matrix has an inverse. And of course this doesn't apply to two matrices, but it does set us up for finding, it does help set us up for classifying square matrices as singular or non-singular. And on top of that, it gives us a more instant assessment of matrices. So let's begin with more numerical examples. So, does this matrix have an inverse? Well, columns 1, 2, and 3 are multiples determined by a value of 4, and because of that, that automatically yields a determinant of 0. And what happens when a determinant is 0? Well, going back a few seconds, if the determinant of the matrix is 0, that means an inverse does not exist, and therefore the given matrix is singular. Now let's move on to another example. So let's take the determinant of this matrix right here. And go ahead and pause the video, figure it out yourself, or you can plug into a calculator for a more instant answer. And we're just going to take the determinant of this matrix. So for every matrix, there's this alternating series of positives and negatives. And we gotta keep that in mind when we expand by rows. So let's expand by row 2 since we have a 0. So we have 3 times the matrix of -2, 4, -3, 1. And anything times 0 is 0. And then we're going to count this. So it's negative in row 2, it's negative plus negative based on this pattern right here. And as a result, we get -3, and this ends up being, the 5 becomes negative based on pattern, and it's another 2 by 2 matrix at 1, -2, -2, -3. Now where am I getting these matrices from? Seriously. So in entry, you eliminate the row and column correspond to an entry. So row 3 is at row 2, column 1. You eliminate all entries in row 2, column 1, and you plug in their residual entries into the matrix. And you do the same thing for 5, while also keeping track of the positive, negative switches. So if we do the math, we end up getting a value of 5. So the determinant of this matrix is not equal to 5. What does that mean exactly? Well, it means that the matrix is non-singular. And when a matrix is non-singular, what does that still mean? It means an inverse is feasible for this given matrix. And that's about it. We are now able to classify square matrices as either singular or non-singular based on short brief analysis.